In this tutorial, we are going to prove mathematically that the magnetic force experienced by a moving charged particle in a uniform and static magnetic field does no work. The magnetic force has the ability to change the trajectory of motion of a moving charged particle in a uniform and static magnetic field. For instance, if we have a uniform and static magnetic field perpendicular to the page and pointing towards the page, we throw a charged particle with a velocity v perpendicular to this uniform and static magnetic field. The magnetic field exerts a force on the charged particle and makes it to move on a circular path. Generally, this magnetic force is given by the Lorentz force law, and the Lorentz force law says that the magnetic force is equal to the product of the magnitude of the charge of a charged particle and the cross product of velocity vector and the magnetic field vector, as shown in equation 1. In this equation, this FB, it stands for the magnetic force vector. We measure it in Newton. And this Q, it is the charge of a charged particle. We measure it in Coulomb. And this V, it stands for the velocity vector. Its units are meter per second. And this magnetic field is represented by letter B. And this B is the magnetic field vector. We measure it in Tesla. And 1 Tesla is equal to 1 Newton per ampere per meter. As we know that the work done by any force can be expressed as the integral of the force times the infinitesimal displacement vector. But we are interested in the work done by the magnetic force. That's why we write the expression for the work as an integral of the dot product of magnetic force and the infinitesimal displacement vector dr, as shown in equation 2. In this equation, this W represents the total work done. It is measured in joules. And this dr, it is the infinitesimal displacement vector. We measure it in meters. Now we write this displacement vector in terms of velocity vector and small interval of time dt, where this dt, it is infinitesimal time interval and we measure it in seconds. Putting this value of dr in terms of velocity and time interval, we get equation 3. And look at the integrand of this integral given in equation 3. This is the dot product of magnetic force and the velocity vector. We call it power. That is the time rate of doing work by the magnetic force. Now, taking the value of the magnetic force from equation 1 and inserting in equation 3 and integrating this integral given in equation 3 over a time interval delta t, where delta t is equal to tf minus ti, Tf is equal to final time and Ti is equal to initial time, we get this expression for the work, and we call it equation 4. Now look at the integrand of this integral. This is v cross b dot v, and as we know from the geometric definition of cross product of any two vectors, the resultant vector of their cross product is always perpendicular to the individual vectors. Hence this v cross b is perpendicular to v, and this implies that the dot product of these two vectors, that is v cross b and v, it must be equal to 0. And putting back this value in this integral given in equation 4, we have this expression, and as we see, the integral on the right hand side, its integrand is 0. Therefore, this total work done by the magnetic force is equal to 0. This shows that the magnetic force performs no mechanical work.